Okay. All right, so let's get started. Hello, everyone. I am Saurabh Saha, and you already know that I'm doing my PhD in theoretical and applied mechanics at Northwestern University. And many of you know me from BUET. I used to be a teacher, a faculty there in the Department of Mechanical Engineering, and many of you are directly my students. So this is our MMRN Beyond series of webinars, and in this webinar we'll try to invite a young researcher from another university other than BUET or its collaborator, who will give a talk on their research, and probably from that you will get some inspiration to do your advanced research or undergrad thesis and all. So in today's talk we have invited Nicolas Aldrete. Nicholas is a dear friend of mine, and he is also in theoretical applied mechanics. He's also doing his PhD in theoretical applied mechanics in Northwestern University. So he's working with Professor Espinosa, who is, if you are working on nanomechanics, you will know that he's a very big name in the field of nanomechanics. And Nicholas is actually working on material science of aspects of it, and also on the biological science aspect of the lab. Um, so he will give a brief introduction on his research and work, but before going into that, I am just giving a very brief bio of the speaker. So Nicholas is from Buenos Aires. I hope I have pronounced it right, Nicholas.
Yeah, Buenos Aires,
uh,
Buenos Aires.
Buenos Aires.
Yeah.
Buenos Aires, Argentina. So in Argentina, Nicholas had a 5-year degree, right? It's a
hmm
BSMS degree in mechanical engineering. So he's also from mechanical engineering. And then he had a job at Tenerife. And after that, he decided to pursue his PhD. And he had a lot of offers from great universities. And then, luckily for us, he chose Northwestern to be his destination. So he has been doing tremendously well. He has published a lot of great papers already and working on very exciting projects, and you will get to see what he's doing right now. And he's also working in collaboration with other professors. One of them is Professor Paulino. He's from Georgia Tech, right? Now he's in
Yeah,
Georgia
now
Tech,
he
right?
moved to Princeton.
Oh, he moves to Princeton.
Yes.
Good for him.
Yeah.
Yeah, so through collaboration, he worked on metamaterial, right? And um,
Yes.
so you'll get to see a lot of interesting work, hopefully today, and I hope you'll get inspired by that. So without further ado, I'd like to request Nicholas to start the talk. Thank you.
Thank you, Surav, for the kind introduction, and hello, everybody. So it's let me just express my gratitude for the invitation, and I hope that whatever I show you inspires you, or it triggers some collaboration or research, or yeah, what scientific networking should be like. So let me just share my screen. Okay. Can you sort of, is my screen visible? Okay. So the name of my talk today is going to be, I named the talk Intersections of Mechanical Metamaterials and Biologically Inspired Materials, which it's kind of an odd name, but I hope you get the gist of it, or I hope that I have structured the presentation in a way that it becomes evident. So as sort of said, I'm doing my third year of the PhD path in theoretical and applied mechanics, and I'm under the advice of Professor Horacio Espinosa. Okay, so the agenda for today that I prepared, I'm basically going to give a brief overview, not a extremely rigorous talk, but I'm just going to showcase different work that I've been doing for the past 3 years since I started. And basically, I'm going to show some work on mechanical metamaterials, particularly on multiscale origami and Kirigami metamaterials, mechanical metamaterials, I should say. And then I'm going to show something that I'm excited about, and we're recently started working on, which is wave metamaterials. and the link with biologically inspired materials, particularly on the phononic behavior of these materials. So I decided to use this kind of a diagram to kind of illustrate like the connections. So so the first part is going to be on origami, but of course here I'm showing like the quintessential origami design, which is like the origami crane, but that was inspired by nature, okay, like the actual crane. And from the origami art of the Japanese, we'll go to Origami Metamaterials and also Kirigami Metamaterials. And then I kind of, or we, like in my line of research, I go back to nature using some concepts from metamaterials, which were originally inspired or researched for wave propagation. And I'm linking those two, or I'm trying to link those two concepts with a focus on biological materials. And all of this can, of course, be used for to create more advanced functional materials. So let's just dive into it. So I'm pretty sure everyone here knows, but just in case, what are mechanical metamaterials? So mechanical metamaterials, they seek to obtain unusual or extremal mechanical properties by exploiting the concepts of motion, stress, deformation, and mechanical energy. Since we are, I believe most of us are mechanical engineers, I'm pretty sure you're all familiar with this. And the field of mechanical metamaterials has gotten a late surge, or it has been getting more and more attention because advances in manufacturing have enabled to create complex architectures at the macroscale and at the nanoscale, as I'm showing in the right panel of the slide. In mechanical metamaterials, you usually have meta atoms, which are like units that repeat, that can deform, fold, rotate, or snap. And this has given birth to a wide array of metamaterials in which, just to name a few, we have cellular and extremal metamaterials, mechanism-based metamaterials, instability-based metamaterials, which they have brought this interesting concept of bucklephilia versus bucklephobia, where if you have the same background as me, we were usually taught that buckling is a phenomenon to be avoided, but there has been a lot of research into actual functionalities of buckling, like how can we exploit buckling for actual good purposes, just to say so. And then we also have topological metamaterials. So within the first subset that of metamaterials that we have studied, we have the field of origami engineering. And the most salient property of origami designs is the property of folding. So origami comes from the Japanese art of paper folding. So that's basically what we try to recover when we do some origami engineering. And this property of folding, this foldability, enables shape morphing. So we can obtain very complex patterns just by exploiting this foldability. And actually, there are some universality theorems that basically say that you can fold pretty much anything. And that's what I'm showing there with the origami bunny, which I don't know how many hours that took, but must have taken lots of hours. Another interesting aspect of this foldability is the property of deployability, which allows to create or enables 2D to go from 2D structures to 3D structures. And this is important for space optimization. And then these origami metamaterials have given or have been discovered to have some very interesting mechanical properties just from the geometrical aspects of their folding. So we have oxidicity, stability, directionality or anisotropy, and tunability. We can change these properties with compression or with deformation. And we also have like the issue of scalability. So we can take concepts, origami concepts from the macroscale to the micro and nanoscale. So it's all very nice. It's easier said than it's done. And this is because the translation of these paper origami concepts into actual origami metamaterials is not very straightforward. The folding displayed, and by that I mean that the folding displayed in paper is very different from the folding with actual or conventional engineering materials. When we do origami, I don't know if you ever played with, I mean, probably you have, like with paper, what you do is basically you locally damage a crease where you actually do the fold. And so this brings down the stiffness in the fold. But can we really do that with actual engineering materials that are going to be subject to more stringent environmental windows? And so when we do that, that creates, when we try to recreate that creates a problem. And people have tried to circumvent that problem or to solve that by incorporating some like mechanical artifacts like hinges or local thinning, or using soft materials at the folds to allow this foldability. So that is one of the issues. The other issue that kind of prevents like the origami metamaterials is the, I mean, it's nice, like, you can do a crane, you can do a bunny, but that's not an engineering material. So how can we use these origami concepts to create something that's actually usable, that can take load, or that can perform under different stresses or requirements, engineering requirements? And so what we did is, it is actually based on a work by one of Paulino's students. We used what is called like the concept of a Miura-Ori tube, where basically there's the most famous pattern in origami is called a Miura-Ori strip. And if you cut those and you assemble them in some way, you can obtain like a Miura, what is called a Miura-Ori tube. And then ingeniously assembling them, you can obtain like aligned or zipper couplings of these tubes. And this gives, you create a 3D origami metamaterial that has interesting properties. So having said that, what we had is, or I frame it in like two challenges. We have like the first challenge, which is can we recreate these folding mechanics, which are very different from paper? And the other challenge is, how do we create origamis, 3D origamis that have an actual functionality? And so those are the challenges, and the solutions is, okay, for the first problem, for the first issue, like the folding mechanics, we decided to go micro and nanoscale origamis. And for the second challenge, we used like the concept of these Miura-Ori tubes to create these 3D origamis. And in the middle, we have multifunctionality, all these properties that we were able to recover that were predicted from basic geometric analysis of these Miura-Ori tubes assemblies. We were able to recover most of these properties. This work was published last year in Small, and it got some interesting news coverage. So how did we do this? So as I said, the first challenge was the challenge of folding. So, and to do that, we went like to the micro and to the nanoscale. So we fabricated via 2-photon polymerization, 2-photon lithography, which was done by the Sridhar Krishnaswamy's group here at Northwestern. They have a lot of experience printing these kind of structures, which are quite complex actually, because you have angles and the panels, like it's you have a lot of that difference between the thickness of the panels and the actual length of the unit cells. So we did this in with a single material, which is an IPD photoresist, and we explored two different kinds of geometries based on some geometric assembly of these Miura-Ori cells. Once we fabricated these structures, we translated them to a glass slide, and we mounted them on a nanomechanical stage, which is a Leibniz stage, which is shown to the right. Okay, to the right here. And we did some compression tests on these structures. And as I said, we were able to recover most of the properties that come from this foldability. So the first interesting properties that we were able to see were the stiffness and isotropy. So basically, once you have this 3D Miura-Ori tube assembly, you have two directions that are foldable, and then you have one direction which is stiffer, which is in the one that you have like the zipper coupling that I mentioned before. And so we were able to observe by doing a very, we didn't do like a simple cycle of compression and unloading with it. like these stepped compression and recovery phases, as you see here, like this. We compress, and then we do we kind of cycle back and forth, and that allows us to study like the stiffness tunability of these metamaterials as the overall compression of the structure progresses. So we were able to see that there are that the stiffness does changes with compression depending on the orientations, and then as you can see here in the pictures, we were able to retrieve that foldability that was one of the main challenges that we had, and what distinguishes origami designs from other kinds of origamis. They also have some very interesting, so you can compress these structures to like 30%, and then you can recover up to like 96%. So that was pretty encouraging as well. And here I'm just showing one of the tests in one of the directions. So this is an Nc2scm test. So you can see how we do. So a first step of modulation, we try to pre-compress a structure, and then we actually, let me just speed it up. We compress, we do these loading and unloading cycles, we keep compressing and so on. So we do get that foldability, and then we can also recover. And as you have probably seen in this video, there's some interesting auxetic effect, and that's one of the other interesting aspects of these structures, which is that they have a tunable Poisson's ratio, which changes with compression, just like the stiffness. And depending on the orientation, the direction that you're looking at the same structure, you can have auxetic behavior or almost close to zero Poisson's ratio. So that is interesting. So here you can see, like to the left, you can see that when I'm looking at this structure from one side, we have auxeticity. And then when we look at it from the other side, we don't have, there's practically zero Poisson's ratio. And same thing with the structure in a different morphology of the structure. Also, what we found when we were analyzing one of these geometries was that these origami designs, as predicted from geometric analysis, they can exhibit what we call like a switchable Poisson's ratio or a reversible Poisson's ratio, which means that the Poisson's ratio changes signs throughout the compression. So these structures, as you compress, they start having like a normal or conventional Poisson's ratio. So as you compress, they expand, but then there's a switch. Something happens in the structure, which is a folding bifurcation. So as the panels fold, they come to a point where they can bifurcate, and that can trigger a negative Poisson's ratio. So as you keep compressing, the structure develops or exhibits an auxetic behavior. So you have both these things, and this is a video of that structure, which has to start again. So you compress, you can see some expansion in the mid zone, and then that folding bifurcation is triggered, and the structure starts contracting laterally as you compress. So that's what we found, and that's this switchable Poisson's ratio. And we also did some modeling, continuum modeling, FEM on these structures, and we were able to recover that. So that's a brief part of the origami work. And so in all of these topics that I'm gonna be touching on today, I like to finish with some opportunities and what we're looking into, or what can inspire for work, which is they have some very interesting wave dynamics, these properties, because as I showed, like in the stress strain curves, some of them exhibit some like strain hardening effective stress strain behavior. Others exhibit more like a plateau or a strain softening. So that can give way to some interesting wave dynamics, like compression solitary and tension solitary waves. And something of this has been shown in a paper that came in Science Advances. And then we also feel that this origami lattices can have some interesting energy dissipation properties from the cyclic loading, elastic buckling, hysteretic effects from friction, etc. And then we can also do some material enhancement, because here we just showed, just origami structures printed with a single material, which is a common to photolithography material, but we can improve these or the properties that we want, for instance, by doing like ceramic coatings or even metallic origami. And then this, on the side of applications, not so much on the fundamental aspects. They can be applied for soft robotics, sensing, actuation, and pretty much everywhere where we have a need for these tunable properties, where we can change them based on the level of actuation, and where we can also leverage the foldability of these origami structures. So the other topic that we've been working on is Kirigami Metamaterials. So I don't know why, but interestingly, within the group, we studied like the metamaterials that are derived from these Japanese art forms and not other kinds of metamaterials. But I don't know if you're familiar with Kirigami, probably you are, but instead of origami where you fold paper, here you introduce cuts on a paper and you derive some shapes. So yeah, people in Japan back in like the Middle Ages, they thought that that was an interesting pastime, so they developed these paper art forms to have some fun. And within the Kirigami engineering, we have two different branches. The first one is called lattice Kirigami, where basically it's kind of like a mixture of Kirigami, where you have cutting of paper or material, and then you fold along certain creases. So I would say it's a mixture of origami Kirigami. And you can give way to certain shapes. And the other one, which is the one we're interested in, is called, was defined in a paper by Callens as Kirigami Engineer Elasticity, where we produce cuts at various locations, but we don't really care about the folding. We just care about using that apparent high elasticity or stretchability that derives from those cuts. And there are two main approaches, which are shown there in the figures 3 and 4. One is the out-of-plane buckling, which occurs in these structures, and the other one is the in-plane rotation. Within that subset, we've been studying a very simple, we focused on a very simple Kirigami object or Kirigami motif, which is basically just a rectangular plate that has C-shaped cuts and then two vertical U-shaped cuts. And as I said, these structures, when they are stretched, basically, instead of failing at the by like some crack propagation in the cuts, what happens is that some bifurcation happens. So these structures buckle under tension, and they give way to some very interesting nonlinear responses, which beyond the stress and strain relationships, they produce some really interesting out of plane shapes, which can be used for different things. So the first work that we conducted in the group was interestingly at the nanoscale, or micro nanoscale, where we used some focused ion beam patterning that created some residual tensions in the substrate, which is a silicon nitride substrate, and this created some residual stresses that caused the material to bifurcate without actually applying any tension, so not controllable. So just you do the FIV patterning, and that generates like the sort of natural emergence of this Kirigami phenomenon. And here we studied like the substrate thickness effect, whether if we have thicker substrates, the phenomenon arises or not. And then we studied some very basic hinge sizes and interactions between cuts. And we mostly focused on symmetric cut layouts. This work was published early this year in Advanced Materials, was on the front cover of it. And this is basically what we observed. So interesting thickness, substrate thickness effect. Once we go to beyond a certain threshold, the Kirigami effect does not appear, but then below a certain threshold, these Kirigami motifs appear. And what we saw on our, I would say, more limited investigations was that we basically can obtain two kinds of patterns, we get antisymmetric modes or symmetric modes. But there are some interesting complex 3D shapes which can be used. And we were able to determine some kind of a landscape where, based on the hinge size and the cut width parameters, which were the only parameters that we were changing, we were able to observe two different landscapes, as I said, an antisymmetric and a symmetric mode. We took this work a bit further, and instead of just studying purely symmetric patterns in all directions, we started playing around with other parameters, and some very interesting things showed up. So, for instance, this is a Kirigami, Kirigami Motif, which is, in this case, it's symmetric with respect to the x-plane, and we were able to observe pitchfork type curves in the sense that so we have this bifurcation, and then the inner panels, which are the ones that we're interested in, the ones that have like these interesting rotations, they emanate from a single bifurcation point. So as you stretch, now we are stretching, instead, now we're not interested in the fib, we're just pulling a Kirigami, and this was done computationally, and then I'm going to show you some macroscale experiments. As you pull, you see the emergence of a single bifurcation or deformation emanating from a single bifurcation point, and then some interesting symmetry breaking properties. So, for instance, in this design, what we have, this is symmetric with respect to the x-plane. Then, if we change that, we have if we have symmetry with respect to another plane, what we observe is that we no longer have bifurcation emanating from a single point, but now we have sequential bifurcation. So as you stretch, one of the plates bifurcates and starts, let's just say, moving upwards, or deforming out of plane. And then as you continue compressing, another plate starts exhibiting that bifurcation, and so on. And we study other more complex scenarios where we play with these symmetries. So in this case, this is what we call an XY symmetry. And again, we recover some interesting properties from bifurcation. And we actually did some, we confirmed these things at the microscale. So we tested some of these patterns at the microscale. And we did some, we use a very classy technique, an old technique, which is the shadow moire technique, which gives some interesting, it allows to map these out of plane displacements very elegantly. So we were able to confirm these FEM simulations at the macro scale, and how just small changes in the Kirigami motif, so playing with asymmetries and symmetries, we can obtain a very wide array or range of out of plane shapes. And why is this important, or why we think that it's important? So it's important because we believe that they can be applied to many different things. So we can do some pattern surfaces, so we can basically collect many of these Kirigami structures into arrays, and we can actuate them under tension to obtain some programmable surfaces. So what we think is that we can do, for instance, in the pattern surfaces, we can affect the wettability, we can affect hydrodynamic or aerodynamic flow modifiers, and they can be used also in heat transfer to change, like locally change, like the circulation of a fluid. Then we can also use it more like in a MEMS, NEMS aspect, like for instance, for optics, we can have like focus variable reflectors, variable mirrors, thin lenses, for instance, that you can change the focus with tension. You can change like the focus of a lens. Also for energy harvesting. And then we had a more crazy idea, which was like we can use this as a steerable solar sail, which basically you can change the angle of light of incoming photons, and that can give you steerability in a type of solar sail application. So this is just a yeah, a very broad thing. And this is just going a bit further on one of the examples. For instance, we can have, as I said, we can put many of these Kirigami together, we can actuate them under tension, and we can obtain, in this case, the design of a Fresnel mirror, in which basically each one of the panels follows like a parabolic law, and that creates a focus. So with this, we can we actually did some ray tracing simulations that were using FEM input. So this is just one application that I wanted to show how we can create these programmable actuators or surfaces, in this case, to have like an interesting optics application. So what is more interesting, and what we are kind of wrapping up now, I'm just going to go briefly on this, is that so we discovered that even with a very simple, indeed with a very simple cut layout, we can obtain a very rich set of possible 3D out of plane morphologies. And depending on the cut dimensions and the relationships, the symmetry or the asymmetries between these cuts, we can obtain a range of 1- and 2-dimensional rotation. So the panels can not only tilt, but they can twist as well. They can warp. So we can so we have like a plethora of a possible design space to actually create functional structures. What is the problem with these Kirigami engineering? So there's, I would say, a complete absence of analytical models that explain the Kirigami phenomenon. At most, I have seen like energetic formulations for a single cut using concepts from fracture mechanics. And so there's an exclusive dependence on computational methods, mainly FEM or MD, if you want to replicate this at the nanoscale, which we are doing with 2D materials, and try an error to obtain a particular design objective. So if you want to design like these Kirigami mirrors, so actually you have to, trial and error until you get what you want. So we're kind of thinking, can we take this a bit further beyond this phenomenological description of the phenomenon and study what really dictates that Kirigami behavior? I mean, what are the relationships between cuts that dictate what the buckle, the post-buckle shape is going to be? And can we obtain surrogate models to design Kirigami structures for a target function? In other words, the question would be, what is a Kirigami pattern that we need to obtain a desired tilt or deformation? And in this sense, we're trying to use some machine learning methods to answer these type of questions. So basically, so we're not trying to develop new machine learning algorithm. We're just trying to apply a machine learning to solve some Kirigami design problems. So basically, we just create a database based on a uniform, based on a Sobol sequence. And then we obtain certain displacement metrics from FEM nonlinear models. And then we're trying to feed that into a framework where basically we try to answer those two questions. First of all, how can we obtain these relationships, these functional relationships that explain how the cuts in a Kirigami dictate their behavior? And then using more from an optimization, design optimization point of view, using forward and backward neural networks to obtain from a desired design or function, the design that we should use to attain that. And just to show like the space, because we've been varying all the possible parameters in this Kirigami, like the thickness, I mean, not the thickness, but the width of the cuts, the length between the hinges, etc. And just doing a very simple like principal component analysis, we've been able to map like this wide space of Kirigami configurations. And here, and if you do that just for the center line of the Kirigami, just for the which would be just for this center line, we can obtain a let's just say like a comprehensive map of like the kind of space of 3D deformations that we are dealing with. And each one of these points in this PCA map does not have like the features of twist in the different edges. So as you can see, even though like this PCA gives like 5 basic deformation modes, which are like U-shaped or like ramps, we have to multiply that or compound that by the warping of the inner panels, which give twists, and that way that augments like the potential design space of the material. So in the interest of time, again, that's basically a very broad description of the work we're doing in the Kirigami Metamaterials. And as I did for the origami part, I want to highlight some of the opportunities that are interesting in this sub-branch of research. So it is very interesting that both the origami and the Kirigami metamaterials, they have some sort of scaling variance. So basically, as I showed, you can retrieve the same properties that you see on paper at the macro scale. You can retrieve them at the micro and nano scale. So we're looking into patterning this Kirigami motif in flexible two-dimensional materials like graphene, TMDCs, and mexines via lithographic techniques. And with that, we are trying to create some reconfigurable meta surfaces with engineered electromagnetic properties. And with that, you can create like metal lenses, light emitters, light absorbers, photodetectors, nano antennas. But you can also alter the electronic properties. Like if you do like band diagrams, you can actually modulate these dispersion diagrams or band diagrams with tension, and also by triggering like these bifurcations, which are known to affect, like when you induce curvature in these kind of materials, you can affect like the band structure and density of states, which has many implications for electronics, but also for heat transfer and phononics. Okay. A bit more opportunities, which is a bit more out there, but in the lab, we're also, as Surab said, there's a side of the lab that deals with cells. And you can also use these kind of pattern surfaces to leverage the concept of kurbotaxis, which comes from the Greek. But basically, what you're trying to do is you're trying to give topographical cues to cellular systems, because it was found that cells can react to topographical cues. So you can basically tune or modulate migration of cells of cells by changing the curvature or the topography of the substrate they're in. So those are the opportunities. And I said, and I'm gonna close the origami and Kirigami metamaterial aspect with the concept of scalability. So here we have our collaborators in a cute picture where they have like this giant origami, this tube origami assembly in a meter scale. But then we can obtain that at the meter, the micrometer, and the nanometer scale. We don't have a meter scale Kirigami, but we have the same thing in millimeter, and then also micrometer and nanometer. And so I post the guy with the question mark here because, as I said, there are many opportunities with these origami and Kirigami metamaterials as we go further down. And for the last part of the talk, I think, yeah, we're doing okay in time. I would like to go back to the these inspired biological materials, which may seem disconnect, but as I conveyed in the first slide today, metamaterials were originally envisioned to alter electromagnetic properties, and electromagnetic properties are basically waves traveling through space. So in the first part of my PhD, I did also some work like pure biomechanics on biomaterials that I decided to join with these concepts that I gained from metamaterials. And I joined them by trying to study phononic behavior in biological materials. So basically, we're trying to study how elastic waves propagate through the complex structures that are found in biological materials. And so this is like the intersection that I was talking about at the beginning of my talk. Phononics is a concept that comes from the acoustic metamaterials community, or also for heat transfer, but we decided to use that from the metamaterials and to merge it with the biological materials to see if we find some interesting intersections there. So what is interesting about the biological materials? Very shortly, biomaterials are very interesting. So they have tremendous, extraordinary and remarkable properties in terms of impact, in terms of strength, in terms of toughness, instead of in terms of modulation of properties with hydration, with temperature, with pH, etc. So they're very versatile materials, and scientists and engineers have been looking at nature for inspiration for actual engineering materials for a long time. So one of the interesting features about biomaterials is that they have a multiscale, how can I say it? A multiscale hierarchical structure. So many different features at different scales, which in turn or as a result give them these very interesting properties. And so this multi-scale and hierarchical structuring kind of reminds reminds of that architecturing of the material that we studied in metamaterials. So again, using those two concepts, we're trying to see if these biomaterials have some interesting wave propagation, elastic wave propagation properties. And this work that we're doing is exactly that. We're trying to study how elastic waves propagate through these biological materials. And to do that, we are using some laser ultrasonic techniques, which you probably have studied somewhere, like in experiments in solid mechanics courses, which are very interesting from the point of view that they are non-destructive and non-contact techniques. So you don't really need to interfere with the material or destroy the material in any sense. And they can be used for characterized like dispersion diagrams. So that would be like wave number frequency relationships. You can characterize anisotropic wave propagation and also mechanical properties. And there can be, we can find some interesting nonlinear wave propagation phenomenon like localization, focusing, etc. And in that sense, I'm just going to show two of the techniques that we've been using. These are ongoing work, but basically, so here you can see we're studying nacre, which is an abalone shell, which Professor Espinosa has studied for a long time. The nacre has a very interesting brick and mortar architecture, and some people have numerically predicted the presence of band gaps in nacre-like materials, but we're trying to study it in the actual material. And for that, we're using a technique called transient gradient spectrometry, where basically what we do is we cross two lasers and on the surface of a material, and these two lasers create a transient gradient, which is basically a transient temperature profile, which generates expansion and contraction of the material, and that launches acoustic waves through it. And then with a probe laser, we are able to pick up that signal. This kind of technique is limited in terms of the frequency that you can study, so up to like 1.1 gigahertz. And so far, that's what we have been studying. But again, you can recreate the actual dispersion diagram of these materials using those techniques. And you can also create or see like scans of how actually these waves, these surface acoustic waves, propagate through the material. And with this, you can detect interesting either phononic band gaps, because then here I'm just showing like a very simple movie in the actual nacre material, but you can filter this and you can map like how the same propagation looks for different frequencies. And with that, you can identify phononic band gaps and interesting non-linear effects, as I was saying before. That's an ongoing work, so I don't have a lot to show that I can show actually, but I just show it would be interesting to show that connection and how we're studying it. So, and again, I would like to finish this with the opportunities of why I think that this work is also important. So, from the role of basic research, how these multiscale hierarchically architecture structures play a role on the propagation of elastic waves. And of course, this has many applied research implications, from mechanical waves to also thermal transport, because basically the phenomenon is also phononic. So you can use this set of experiments and also some modeling aspects to also infer on the phononic properties, but from a heat transfer point of view. And with that in mind, I would like to close the talk. Again, I hope I successfully conveyed like this connection, which as I was doing the talk might seem weird, but I think they are. I mean, I do believe that these things are connected somehow. Yeah, and I would like to finish by acknowledging many collaborators, colleagues, professors, and different support sources for this research. And I hope everyone enjoyed the talk and that I was clear enough. And yeah, we can move on to the question section, if that's okay with Surab.
Thank you so much, Nicholas, for this wonderful talk. I'm sure we have learned a lot, and those are really interesting works, actually. And it seems that they have a lot of applications as well. So moving on to some question. One question that I already have is from Khan Mohammad Rabbi. He is also a PhD student in his advanced stage. So he asked the question that, hi Nicholas, thanks for your presentation, very exciting work. And he wants to know whether you guys have conducted any dynamic tests like fatigue analysis on the origami motivated 3D structure. If so, if you can comment on the modes of failures that this type of material will undergo.
So no, we have not conducted any fatigue tests on this origami structures. So that'll be the answer to the first one. I do think it's an interesting property to study. And the second question was, the failure modes.
Yeah.
So typically in these plate and sort of like shell metamaterials, the failure modes occur at the joint, so at the creases where the panels meet, and there you do have some plastic collapse. I mean, at least in the structures that we observe, you do have some plasticity, so and some tearing, but always the failure occurs like at the joints. In one of the designs, so that would be the predominant failure, like in the foldable designs, the ones that I showed. But we also studied another structure which, how can I say, which doesn't exhibit that foldability property. So it's like a stiffer origami, and that one actually has a very interesting mixture of like buckling and cascading plastic collapse. So the rows, each row of these Kirigami metamaterials start collapsing plastically, and yeah, it's like you end up with like a very thin origami where you don't fold, it just collapse row by row. I don't know if I'm being clear, but I do think there's some interesting work to be done in terms of how these materials fail, and of course in the fatigue regime with repeated loading.
Okay, thank you, Nicholas. So Vivek, you wanted to ask a question.
Yeah, I think someone was before me. He can go ahead and then I can ask the question.
No, I think Rabbi was before you, so I asked Rabbi's question, so you can go ahead, right?
Okay. Thank you, Nicholas, for the nice talk. It was interesting. So a couple of questions. It's not going to be a question. It's going to be a discussion session. I might follow up later on. So I have a question that what type of materials that you use? Like if I missed something, like is it, is it like some PDMS or any kind of what kind of polymer or?
So for the origami, we used it's IPD, which is like the commercial name. I think it's commercialized by Nanoscribe. So that's a basic two photon lithography material. Yeah, I don't know of any like salient properties of that material. And then for the Kirigami, we just patterned like the fib at the microscale. It was like a silicon nitride. Yeah, typical microfabrication techniques. Yeah.
Yeah. So one of the challenges, I think you mentioned that this is like interesting. This is going to be interesting application in soft robotics. So my current project is in soft robotics. One of the challenges that we are facing, that people have been doing, like your group and other groups, like across the, like even there, like Caltech, UC Berkeley, and also in people are doing like interesting origami and kirigami structures. But the next step is to generate locomotion out of it. That's something that we have been like, we don't know how to do this. Like we have like individual structures that showing some sort of folding or bending, but how to put them together and then let it move like over the time. Like it could be some sort of stimuli, or it could be some sort of like mechanical loading or anything. But we still don't understand. Like, do you guys have any plan on that direction, or like any ideas like how things are going?
So we have been, I mean, not actively looking into like these active materials, like activate them like via temperature, pH. I think there has been some work by Professor Cohen in Cornell, and he's looking into that. But as you said, there are many issues with that, especially like with the time of actuation. Like if you do temperature, yeah, sure, it actuates, but like it's very slow. So I mean, yeah, you can also do that like with pH and different things. I think it's an interesting field of research, but we are not looking actively into like this active.
One of the follow-up thing that yeah, that's completely fine. But one of the follow-up thing that well, we haven't started, like we didn't really do any origami or kirigami structures, but we are looking into it. Like yeah, because like those gives us like very different deformations, and we can deformation like asymmetrical deformation of two different colors. I mean, to generate locomotion, you have to have asymmetry. Otherwise, it's not gonna symmetrical is gonna come back to zero.
Right.
That's something that we are looking into. Do you have any good? Do you have any recommendation to start somewhere, like how to come up with a design, or like you have these designs for Kirigami and some of the, like good point to start if someone wants to start?
So let me just say that I wasn't able to hear you very well. Yeah, maybe if you can come closer, like to the microscope. Microscope, the microphone.
Yeah.
Sorry. Yeah.
Like, do you have any recommendation to get started in this sort of designs, design space that we can look into how to design?
So more in the. So I would say start. So yeah, that's a tough question. So I would say start with the application that you have in mind first, because as I said, like you can use this for many different things, and based on that, you can define. Yeah, so based on the application, you can define like the kind of metamaterial that you will look into. Like for instance, in the case if you're trying to design some deformable lenses, or I don't know, something that you require this out of shape deformation, then look into Kirigami. If you want some soft actuation, go into, I don't know, perhaps like Origami Metamaterials, or different kinds of metamaterials as well. And then I don't know if your question was aiming at
I mean, how to get started in like origami and Kirigami design thing. Like, how do you like? Is there any like good like reference books or reference papers?
Or okay. I see.
Designing of these kind of structures. Like,
so for origami, there's a really good book. Okay, so one person that does a lot of origami is called Lemaine, Victor Lemaine. I would suggest he's a professor at MIT. He actually works with his father, who is also a professor at MIT, I think. He has a very good book on like the mathematical aspects of origami, so that's always a good place to start. In Kirigami, I don't know of any like books or like deep mathematical treatment of it, but I would say anything that has to deal with instabilities in materials is a good place, because that's basically what is interesting in Kirigami Metamaterials. And then there's one more book on origami, which, like in the hardcover, they have like origami fishes. I forgot the name, but I would say just go with Lemaine, and you can start from there.
Okay, thanks. Yeah, that was useful. Thank you.
Thank you, Vivek, for your question. So I have another question from Riyaj. So Riyaj, thanks you, Nicholas, for your talk. So his question is that in biological metamaterials, have you considered bosonic systems, or is there an example of boson fermion couple systems for the metamaterials?
Wow, that's a good question. So no, we have not considered bosonic systems. Is there any examples of boson fermion couple systems? No, I mean, not that I know of. Probably there is. I wouldn't say that I'm the right person to answer that. It's not a literature that so that particular literature, I haven't seen it or investigated. So maybe there is, but I honestly don't know.
So or optical metamaterial, like any kind of optical
Optical
metamaterial?
metamaterial, there's a lot of research in optical metamaterials. So these meta lenses are like, I would say, like the prime manifestation of these optical metamaterials, where they actually, you can have like a flat lens and without any sort of stretching or anything, so you don't look to deform the structure, but you can alter the electromagnetic properties. So instead of dealing with like geometric optics, you're dealing like with the more physics optics or electromagnetic optics. Or there's a lot of research into that.
Another question he asked is that in terms of nonlinear simulations that you did, have you done any kind of perturbation or any other perturbation method or that sort of thing?
I mean, no, but we have found that so no perturbation, but what I can say about the perturbations is that we have found that there is some very interesting, or they're very highly dependent, like these origami designs are very highly dependent on the initial imperfection that you use to trigger these bifurcations. So depending on the kind of perturbation, initial perturbation that you give to the system, these can affect the subsequent or the final state of the Kirigami after you stretch it. So I have shown some of that in one of the papers, and there's definitely a lot more to study into how you design these original perturbations to end up with what you want.
Okay, thank you.
Yes.
So we are almost at the end of the talk. Anyone else want to ask a very quick question? If you want to ask, like, you can just jump in and ask it directly without sending a message. That would be fine too. Since you're out of time. All right. Okay. Thank you so much, Nicholas. Yeah, then I think there is no question. It was a wonderful, wonderful talk, and we, from our group members, we're really grateful that you have managed the time from your busy schedule on a weekend to give us a really nice talk. And we can expect this kind of webinar in the future, and we are really hoping that we can invite you for another round of talks sometime later in future.
Okay, for sure. Yeah, give me time to collect more results.
Of course.
Yeah, but yeah, thank you so much for the invitation, Surab, and for everyone here for attending.
Yes, I also thank the students for coming to this talk. Best of luck, Nicholas, for your PhD research. Thank you so much.
Thank you guys. Thank you for attending, and yeah, you're welcome to write me, shoot me an email for follow-up, or yeah, this can give rise to interesting collaborations or discussions. I also welcome those. So Thank you, everyone. And yeah, I hope you enjoy the rest of the weekend.
Thank you so much. So this talk will be uploaded in our official channel, and once it is uploaded, I will send it to Nicholas, and I guess the participants, you will find it on our Facebook page and website maybe, right?
Okay.
So thank you so much. Goodbye and have a nice
Thanks.
weekend.
Bye.
Bye.